PDE-2D is a partial differential equation solver that was developed by Granville Sewell of the University of Texas El Paso over a period of nearly 50 years. Despite the name, PDE-2D actually solves problems in 1D intervals, completely general 2D regions with curved boundaries, and a wide range of simple 3D regions. It solves very general systems of nonlinear, steady-state, time-dependent, and eigenvalue partial differential equations with very general boundary conditions. It has an easy-to-use graphical user interface and produces many types of graphical output and has all the flexibility of Fortran. Here is a list of over 250 journal publications and books in which PDE-2D or its predecessors 2DPEP and PDE-Protran were used to generate some or all of the numerical results. And here are the 3 graphical user interface examples and the 15 interactive driver examples. My 2018 John Wiley book, Solving Partial Differential Equation Applications with PDE-2D, has the most complete documentation on PDE-2D. This book shows how to use PDE-2D to solve a wide range of applications, including beam and plate bending, diffusion and heat conduction, image enhancement, math finance, elasticity, fluid flow, the Schrodinger equation, and minimal surfaces. All versions, including the source code version, which should work with any Fortran NATI compiler, are free now. If you want the source code, please send me an email here. Pre-compiled versions for Windows and Macs, which require specific Fortran NATI compilers, can be downloaded here. It is very important to watch the installation video linked here, no matter which version you use. Actually, there are 2 very different user interfaces. The graphical user interface that we will discuss first is a lot easier to use and gives you fewer options and chooses many more defaults than the interactive driver interface we will discuss later. But in either case, you end up with a Fortran program which you can edit and modify many options there. To invoke the GUI, you type PDE-2D_GUI, then the name you want to give the program. With the GUI interface, you can only invoke the PDE-2D collocation methods, which means that for 2D problems, you're limited to a wide range of simple regions, also in 3D. We'll see more precisely what that means later. If you have a complicated 2D region, you'll have to use the interactive driver interface to access the Galerkin methods. The first choice you have to make with the GUI is to decide if you want to solve your own problem or one of 3 prepared examples. We're going to work through example 1, which is a 3D eigenvalue problem in half of a torus. The equation is the Laplacian of q minus q over the square root of x squared plus y squared plus z squared equals lambda q. If you choose one of the examples, PDE-2D will give you the answers to all the questions, so all you have to do is hit the continue button and watch. But in general, the GUI gives you the option of solving 0D, 1D, 2D, and 3D problems, steady-state, time-dependent, or eigenvalue problems, up to 8 partial differential equations. If you need to solve more than 8, you'll have to use the interactive driver interface. Now, the PDE-2D user does not need to be a Fortran programmer. However, the PDE and boundary condition coefficients and so forth will have to be input as Fortran expressions, so you'll need to know how to write simple Fortran expressions using the usual arithmetic operators, but they are similar to MATLAB expressions and many of the same basic math functions are available. Here we can define parameters which will be used elsewhere in the program. I'm defining R0 to be the toroidal major radius and R1 to be the poloidal minor radius. Now here we define the 3D region using parametric equations. When I said earlier that PD2D solves problems in a wide range of simple 3D regions, that means any region that can be defined with x, y, and z as functions of parameters p1, p2, p3 with constant limits on the parameters. So for example, p1, p2, p3 could be cylindrical coordinates r, theta, and z, or spherical coordinates. Here we are using toroidal coordinates where p1 is the toroidal major angle, p2 is the poloidal minor angle, and p3 is the distance from the center line. We want a 9 by 9 by 9 finite element grid. The toroidal angle p1 goes from 0 to pi because the region is only half a torus. The poloidal angle p2 goes all the way around from 0 to 2 pi, and the distance from center line p3 goes from 0 to r1. By default, the grid will be uniform, but we'll see that it is easy to make the grid non-uniform later. We want to find the eigenvalue closest to a user-specified number. We want to call the unknown Q. And here we could ask to calculate integrals of functions of the solution and its derivatives. We don't want any now. Now we actually define the PDE. There's only one. F1 equals lambda rho Q. Rho is just 1. F1 is the Laplacian of Q minus Q over the square root of x squared plus y squared plus z squared. Notice that despite the fact that the region is defined in terms of toroidal parameters, the PDEs, boundary conditions, and everything else can be defined in Cartesian coordinates. So once you have defined the region using parametric equations, the rest of the input is absolutely as simple as if the region were rectangular. The equations are written the same way regardless of the type of region. Here we define the boundary conditions. These are at P1 equals 0 and P1 equals pi. Those are the two flat ends. P2 is the poloidal angle. We're defining periodic boundary conditions on P2. P3 is the distance from the center line. At P3 equals 0, there's no boundary, so no boundary condition. On the outside curved boundary, P3 equals R1, we set Q equals to 0. The GUI will normally decide what output to give you. The interactive driver will give you a lot more output options, but here we have to define what cross-sections we want. PD2D gives you all the flexibility of Fortran. For example, any PDE or boundary condition coefficient can be defined using a Fortran function, and the function can be defined separately. A function could go read a file and interpolate, for example. And we're done. Now, whether you use the GUI or interactive driver interface, all PD2D does is create a Fortran program for you, which can be compiled and linked to the PD2D library and executed. Let's look at the Fortran program created by this GUI session using an editor. It's called exam1.for. It looks like a complicated program, but it's all written for you automatically. The parameters you defined during the GUI session appeared here. For example, here we asked for a 9 by 9 by 9 finite element grid. Lines that are lowercase normally should not be touched by the editor. Uppercase is normally input from the GUI. You can modify the grid now as documented above in the comments. For example, it explains how you can easily make the grid non-uniform now. The GUI chooses many parameters for you automatically by default. For example, here it chooses the linear system solver to be a sparse direct method. You can change that now. Or for example, if instead of calculating one eigenvalue with eigenfunction, you want all eigenvalues without eigenfunctions, just change I type to 4 as documented above. Now let's skip down to the definition of the PDE coefficients. Here they are. F is the Laplacian of Q minus Q over the square root of x squared plus y squared plus z squared. Rho is 1. The form of the PDE is defined above in the comments, so you can easily modify them here. Here are the boundary conditions. Those can be modified also. Now, in addition to the graphical output that PDE2D creates itself, PDE2D will also generate a MATLAB program automatically for you to do further plots, and this program can be modified to create any other plots that MATLAB can make. All you have to do to generate the MATLAB program is to remove all of the C exclamation mark comments with an editor. Now when we run this program, it will create a MATLAB program for you automatically. Now we're ready to run the program using Run PDE2D. Run PDE2D compiles, links, and executes the program. Here it's printing out the eigenvalue that was found to be closest to the user-supplied number using the inverse power iteration. The PDE2D graphics will be in a file called exam1.ps, so let's look at that using Ghost View. Here is the 9 by 9 by 9 finite element grid in the parameter space. And here are some cross-sections of the eigenfunction at P1 equals constant. P1 is the toroidal angle, so these are some circular torus cross-sections. Now, as I said, PDE2D automatically writes a program pd2d.m, which contains MATLAB commands to produce certain plots and which can be modified to produce other MATLAB plots. Here's the program. It's all written for you automatically. Now let's run it. The MATLAB program pd2d.m reads the data from pd2d.rdm and produces the following plots. These are P3 equals constant cross-sections. The eigenfunction value is coded by color. Here it's green. Green is 0 because the boundary condition on the curved boundary is 0. Here are some other cross-sections. Red is the highest value, blue is the lowest, so you can get an idea of what the eigenfunction looks like by looking at several of these cross-sectional plots. It will also do constant P1 and constant P2 cross-sections if you request them. Here's the finite element grid. And here's the output grid. Now let's look at the other user interface, the interactive driver. The interactive driver interface is more verbose. It gives you more options and chooses fewer defaults than the GUI, but you end up with essentially the same type of Fortran program. To invoke the interactive driver, you simply type PD2D in the name you want to give the program. The interactive driver has 15 prepared examples. If you choose one of these, it will give you not only the questions but the answers. We're going to choose example 8, which is a fluid flow problem. A fluid is flowing through a pipe around a bend. We use the Navier-Stokes equations with a penalty method formulation. It's a 2D problem. We have to use the Galerkin method because of the region. We want double precision. Alpha is the penalty method parameter. For a lot of parameters, the definitions are inside a box called the fine print. It will just say if you don't want to read the fine print, use the default or a suggested value. The user basically defines the region through an initial triangulation. For rectangular or simple regions, the initial triangulation can be defined automatically for you. Here we will define the initial triangulation by hand. I'm actually going to read the data from a file I prepared beforehand called pd2d.in. If I input a pound sign, it will start reading from this file until it encounters another pound sign. We want 200 triangles in the final triangulation. PD2D will automatically refine the initial triangulation until there are 200 triangles. The refinement can be adaptive, or you can specify a function, as I'm doing here, which is largest where you want the triangulation to be most dense. The suggested linear system solver is isolve equals 4, the sparse direct methods. We'll use that, and fourth degree elements. The problem is steady state. It's not linear. There are two equations. We'll call the unknowns U and V. Now the PDE coefficients are defined. I'm going to read them from a file again to save time here. The initial values can be defaulted. On the inlet boundary, we define the velocity components U and V. On the rest of the boundary conditions can be defaulted. We want a 20 by 20 output grid. Here you have a lot of output options. We're only going to do a vector plot of UV, the velocity field. And we're done. Again, whether you use the GUI or interactive driver interface, the final result is a Fortran program which is written for you. And again, you can make modifications and corrections to the Fortran with an editor. Again, all the parameters you input are here. They can be changed at this point. The questions you were asked during the interactive session are repeated as comments. Typically, the user will create a program using either the GUI or interactive driver interface, and then for a long time make changes directly to the Fortran. You don't need to rerun the interactive driver or GUI unless you make major changes, such as going from a 2D to a 3D model. And again, you don't need to be a Fortran programmer to make these changes. All you need to know is how to form basic Fortran expressions. This time we won't bother creating MATLAB graphical output. We'll just look at the graphics generated by PD2D itself. It uses Newton's method to solve the nonlinear system. It converges in 10 iterations. And we can look at the PD2D generated graphics using Ghost View again. Here is the initial triangulation. Here's the final triangulation. And here's the fluid velocity field.